Hello and welcome to lecture 21 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to learn the very important concept of density of states. Last time we derived an expression for the concentration of free electrons, which are electrons in the conduction band. In this lecture we're going to rederive this expression, but now using a different strategy that involves the very important concept of density of states. Still in the previous lecture, we calculated the total number of free electrons by adding up the probabilities of occupation of all orbitals of the conduction band. So this sum runs over all orbitals of the conduction band, and this term is the Fermi-Dirac distribution, which gives the probability of occupation. Now recall that the only information about the orbital that enters into the Fermi-Dirac distribution is the energy. So that means that orbitals with the same energy have the same probability of occupation. So instead of adding the contributions of all orbitals, orbital by orbital, we could instead group all orbitals with the same energy, in other words, all orbitals with the same probability of occupation, and obtain the contribution of these orbitals with the same energy to this sum in one stroke. Now let me show you this idea using an example. So suppose we have the orbitals of the conduction band, and then we select three orbitals that I'm going to name alpha, beta, and theta. And we selected three orbitals with the same energy, which I'm going to call epsilon example. So labeling the energy of the orbital alpha as epsilon alpha and of orbital beta epsilon beta and so on, we have that all energies are equal to this energy of the example. So in the previous lecture, we calculated the sum adding orbital by orbital. So we did a sum that looks like that. We added all orbitals, then we came to the contributions of orbital alpha, the contribution of orbital beta, and then the contribution of orbital theta, and kept summing. So that's what we did in the previous lecture. But if these three orbitals of our example had the same energy, then this number is the same as this number and is the same as this number. They are all the same number. In other words, they are the number that the Fermi-Dirac distribution returns for the energy of the orbital, which we are calling epsilon example. So instead of adding this same number three times, we could just get the number of orbitals that has this energy and multiply by the probability. So this is the way we're gonna evaluate this sum in this lecture. Notice that we are doing exactly the same sum we did in the previous lecture. But now, instead of adding orbital by orbital, we're gonna group all orbitals with the same energy and obtain their contribution in one stroke, like here, by taking the Fermi-Dirac distribution and multiplying by the number of orbitals with that energy. So to do that, we can consider a range of energies. So suppose we consider the range of energies between the energy epsilon and the energy epsilon plus delta epsilon. So we need this delta epsilon to be sufficiently small so that all energies within this range will have the same probability. So this, mathematically speaking, this step in the energy has to be considered as infinitesimal for the Fermi-Dirac distribution. So the Fermi-Dirac distribution for all energies evaluated between epsilon and epsilon plus delta epsilon must be the same for our idea to work. And that's easy to do. Later on, we're going to make this term infinitesimal. But assuming that that is already done, we define this term as being the number of orbitals with energy between epsilon and epsilon plus delta epsilon. So that was our number 3 in the previous example. So now we can evaluate the sum by taking the number of orbitals with energy between epsilon and epsilon plus delta epsilon, multiply this number by the probability of occupation. So all orbitals within this range have this probability of occupation. So we take the probability, multiply by the number of orbitals, and we have the contributions of all orbitals within this range. So all we need to do is to sum the contributions over all possible energy ranges. That's why this sum here runs over the energies, no longer over the orbitals. So a major advantage of this approach is that now we have only a single variable, the energy. Recall that this sum is a triple sum, so we had a triple integral. Here we're going to have a single integral because we are grouping all orbitals with the same energy and taking their contribution in one stroke. Now we are ready to define the density of states, which is the main subject of this lecture. Using the language we defined in our course, we shouldn't call this density of states. We should call it density of orbitals. But density of states is more common in the literature, so I'm going to call it density of states. But keep in mind that we are actually speaking about a density of orbitals, because by definition, the density of states is the number of orbitals with energy between the energy epsilon and the energy epsilon plus delta epsilon divided by delta epsilon. So this is the density of states evaluated at the energy epsilon, and this is the definition of the density of states. So this is the same definition for any kind of linear density. Suppose, for example, that you had a rope and you wanted to measure the mass density of this rope. What would you do? You'd get a small slice of this rope. So the small slice, it's a small length, plays the role of the small variation here of the energy. And you would measure this rope to obtain the mass of this little section of rope. So the mass would play the role of the number of orbitals. So this is the same idea of density, but applied now to the number of orbitals. Now, using the definition of density of states, we can replace this term, which is the number of orbitals with energy between epsilon and epsilon plus delta epsilon, in terms of the density of states. So it becomes the density of states times the variation delta epsilon. And of course, I already mentioned, we want this term to be infinitesimal because we want all orbitals within this range to have the same probability of occupation. So the function here cannot change when we move from epsilon to epsilon plus delta epsilon. And since this is already in the form of a Riemann sum, when you take the limit of this step going to 0, we already get an integral. And notice that I'm using here explicitly the domains of the integral. Remember that we have to integrate over all possible energies. And since we want the number of free electrons, we need to integrate over all energies of the conduction band. So we start with the lowest energy, and we can go all the way to infinity, because this term here will go to 0 as the energy goes to infinity. So even though the highest energy is not infinity, we can integrate all the way to infinity because the Fermi-Dirac distribution goes to 0 as the energy increases. Okay, so then taking this limit of delta epsilon going to 0, this sum reduced to the integral, and we have an expression for the number of free electrons. In other words, the number of electrons in the conduction band. Okay, now we need to find the density of states, which is our main job in this lecture. To show you the strategy that we use to obtain the density of states, I'm going to assume a two-dimensional ideal gas. And I'm going to do that just because it's easier to see. The drawings are simpler. As soon as we understand how we obtain the density of states of a two-dimensional gas, it's going to be easy to extend the idea to a 3D gas, which is our main goal since a semiconductor is a 3D material. Now, recall from lecture 7 that where we consider a cube, so a 3D box, that each orbital was indexed by 3 natural numbers, and the energy was given by this expression. Now, if we consider a 2D system, then we lose one of the natural numbers. Remember from lecture 2 that when we consider 1D system, 1D quantum well, we had just one natural number. Then we went to 3D with 3. If we had considered a two-dimensional box, we would have that each orbital would be indexed by 2 natural numbers, and that would be the expression for the energy. So we're going to consider first a two-dimensional system. So to find the density of states, we need to find the number of orbitals with energy between epsilon and epsilon plus delta epsilon. We need to find the number of orbitals within a given energy range, because the density of states, as we've just seen, is defined in terms of this number. Now, since each orbital is specified by a given combination of natural numbers Cx, Cy, we could represent each orbital in a plot of Cx against Cy, placing a point in every possible combination of natural numbers. So this point here represents the orbital 1, 1, this point represents the orbital 1, 2, this point represents the orbital 2, 1, this point represents the orbital 2, 2, and so on. So if you do that, our job is reduced to counting the number of these points, and that's what we're going to do. Notice that I also place points in the other quadrants, so I'm considering here negative numbers. These points do not represent physical orbitals, but we're going to consider them in our calculation, and then we're going to divide the result by 4 because only this quadrant applies. We're just going to do that because it's easier to visualize if the system is symmetric. Okay, now suppose that we look at the same plot but from a distance. So we zoom out and look at the plot, and we can no longer distinguish the individual dots here, the individual points, because we are looking from afar. And recall what is our job. Our job is to find the number of orbitals within a given energy range. So to find this, we need to identify how the energy is manifested in our plot. Notice that the only information about the orbital itself that enters into the energy is the sum of the squares of the numbers. So that means that the information about the energy is given by the distance of the point to the origin. In other words, we can draw a circle with radius r, then all orbitals on this circle will have energy epsilon, which will be related to the radius r through this expression. So we could think of epsilon being here, and here we have r squared. Likewise, if we draw a radius which is a little bit longer than the initial radius, we're going to be identifying the orbitals with energy epsilon plus delta epsilon. So all orbitals with energy between epsilon, so with energy here, and energy epsilon plus delta epsilon with energy here, will fall inside this ring. So our job is reduced to finding how many orbitals are inside this ring. And to do that, we can define a function eta of r as being the number of orbitals, or the number of points, within a disk of radius r. So if we define the function eta of r in this way, when we express this function in terms of the energy epsilon, where the energy epsilon and the radius r are connected through equation, this term is the square of the radius, and this term will be the energy epsilon. Then, when we express this function in terms of the energy, we will be obtaining the number of orbitals with energy lower than epsilon. And to understand that, just consider that, for example, we have a disk here of radius r, and eta of r would be the number of points inside the disk, the number of orbitals inside the disk. So the energy epsilon is the energy associated with the circle that is delimiting the disk. So all the orbitals within this circle will have energy lower than the energy epsilon, because all orbitals will have a distance to the origin that is lower than the distance set by the radius r. And with this definition, then the number of orbitals, the number of points inside this ring, which I'm representing as this term here, will be given by the number of orbitals inside the disk of radius r plus delta r minus the number of orbitals inside the disk of radius r. So if we take the number of orbitals inside the larger radius minus the number of orbitals inside the lower radius, we get the number of orbitals between them inside the ring. And likewise, using this definition, then the number of orbitals with energy between epsilon and epsilon plus delta epsilon will be given by the number of orbitals with energy lower than epsilon plus delta epsilon minus the number of orbitals with energy lower than epsilon. Now to find this function, in other words, to find the number of orbitals within the disk of radius r, we can assign an area for each orbital. So we can draw a little square here in such a way that the squares of each orbital will connect, filling up the whole area of the plot. If we do that, we are assigning an area for each orbital, and then we can obtain the number of orbitals within the disk as being the area of the disk divided by the area assigned to each orbital. But the area of this little square is 1, because the side of the square is 1, since the distance of each orbital to each other is 1. So if I place another square of side 1 here, I'm going to have 0.5 plus 0.5, so the squares will connect. So that means that the number of orbitals within this disk coincides with the area of the disk. So the area of the disk is pi times r squared, and we are dividing by 1 here just to emphasize that we are divided by the area assigned to each orbital. But we have to multiply by 2 because each orbital here actually represents 2 orbitals because of the spin. So we need to take the spin into account. So this 2 here comes from the spin. But then we have to divide by 4 because only this quadrant um, contributes to physical orbitals. So now we have an expression for the number of orbitals within the disk. Now we simplify the expression, and now we need to make the change of variables to turn this expression into the function that gives the number of orbitals with energy lower than epsilon. And to do that, we just need to recall that if we fix the radius, if we fix Cx and Cy, then we can identify epsilon as being the energy associated with this radius. So we could place epsilon here, then we are going to have r squared here. So we obtain r squared by moving this term to the other side and this term to the other side, so we obtain this expression. So this expression connects the radius with the energy through this equation here. So replacing r squared with this expression, we obtain this expression. So this, everything inside brackets here is r squared. So now we have an expression for the number of orbitals with energy lower than epsilon. And this is the term we want. Remember, we want the number of orbitals with energy between epsilon and epsilon plus delta epsilon. So that is just the number of orbitals with energy lower than epsilon plus delta epsilon minus the number of orbitals with energy lower than epsilon. Now recalling the definition of density of states and expressing this term in terms of this term, we get this expression for the density of states, which is just the derivative of this function. So to get the density of states, we take delta epsilon in the limit that it goes to 0. This expression reduced to this derivative. We already have an expression for eta, it's this function here. So all we need to do is to derive this function with respect to the energy. That's very straightforward and gives this expression here for the density of states of a two-dimensional system. Okay, now we can follow the same strategy, but in a 3D system. If we're considering a 3D system, then the squares will turn into cubes. The area of the disks will turn into volumes of spheres. This function now is the number of orbitals within the sphere of radius r. And when you express it in terms of the energy, it becomes the number of orbitals with energy lower than epsilon. And now to take the number of points inside the sphere, we take the volume of the sphere, which is this term, and divide it by the volume of the cube, which is again 1 because the cube has side 1. Now we remember that each point actually represents 2 orbitals because of the spin, so we multiply by 2. And we recall that we can divide the sphere now in 8 parts, and only one of these parts will have Cx, Cy, and Cz positive. So we have to divide by 8 because only natural numbers represent physical orbitals. And then we get this expression when we simplify. Now we use again this relationship between the radius and the energy to express the number of orbitals with energy lower than epsilon. So we just need to use this expression for r squared. So we replace it here, so we get this expression for the number of orbitals with energy lower than epsilon. And then again, to get the density of states is exactly the same idea. We need to derive the number of orbitals with respect to the energy. So we need to derive this expression with respect to the energy. If we do that, we obtain this expression. There is no mystery. Okay, so we have now an expression for the density of states of an ideal electron gas. Now recall from the previous lecture that we need to do two modifications to connect the ideal electron gas with the gas of electrons in the conduction band. One modification is to replace the mass with the effective mass to take into account interaction with the atomic structure. So that's very straightforward. We just replace this term with the effective mass. And the other modification is that our reference energy is no longer zero, but epsilon c. So the way we derive this expression, we consider that the origin represented an orbital with energy zero. But now we need the origin to represent an orbital with energy epsilon c. Another way of looking at this problem is to consider that the way we have constructed the problem, the density of states evaluated at the origin, or in other words, for epsilon equals 0, is 0. But now we need the density of states evaluated at the origin epsilon c to be 0. So both ways we look at the problem, we conclude that we need to replace the origin with epsilon c. So to do that, we just need to replace the square root of epsilon with the square root of epsilon minus epsilon c. So with this replacement, when we evaluate the density of states at the minimal energy, epsilon c, we get 0, like we get when we evaluate the density of states at the minimal energy, which is the energy at the origin. So with these two modifications, this expression is now adapted to the system gas of electrons in the conduction band. In other words, a free electron gas. Now we have all the ingredients that we needed, and the problem is only a matter of evaluating the integral. So we begin by simplifying a bit the expression for the density of states. So the L squared we extract from the brackets, so it becomes L to the power of 3. The 8 we expressed as 2 times 4 and extract the 4, and we end up with this expression. And we also use the Boltzmann approximation that we discussed in the previous lecture to simplify the Fermi-Dirac distribution. Now we just put the pieces together. So we use this expression here for the Fermi-Dirac distribution, so that becomes this expression. We use this expression for the density of states, it's here, and we have the integral. And now we extract all terms that do not depend on the energy from the integral. And now it's just a matter of evaluating the integral, so I'm just going to give you the result. So that's the result. You can check that's the same as that we obtained in the previous lecture. And then we again follow the same idea of the previous lecture. We define N as the concentration of free electrons, so it's the number of electrons divided by the volume. So we end up with this term for the concentration. We define NC like that, and we obtain exactly the same result of the previous lecture. And it is the same result because we have done exactly the same sum. But last time we did the sum by taking the contribution of all orbitals, orbital by orbital. And now this time we grouped all orbitals with the same energy and took their contributions in one stroke using the density of states. And that's it for today. So next time we calculate the concentration of holes following a very similar strategy to the one we developed in this lecture. So I see you next time.